Hello to everybody. It is 9 o'clock, so it's time to start with the webinar Bevel Gear Design in KISSsoft. My name is Jürg Langhardt. I'm Director of Global Sales of KISSsoft, and it's a pleasure to me to make the webinar for you. Some information in the download area, you will find the presentation, which also is shown now in the webinar. And if you have any questions, feel free to enter them in the chat functionality. And at the end of the webinar, I will try to answer on them. So let's now start with the presentation. First, I would like to go into the scope of KISSsoft. And when we look at a classification in bevel gears, we can see the straight bevel gears. I differentiated between cut and forged bevel gears, then skewed bevel gear and serral gears, and then spiral bevel gears, the ones without offset bevel gears, and the one with offset means the hypoid gears. So this is the scope of the KISSsoft software as well. I would like to start then with the spiral bevel gears. It's the classification of face hobbing and face milling bevel gears. I will not go now too much in manufacturing or in bevel type explanations. I really like to focus on the KISSsoft part, and now I show you an example of a bevel gear face milling, and then we look at the overview graphics. So now we can see this typical taper two-step for face milling. All the apex close to the crossing point. We can also see for bevel gears, 3D models are available, and we can also see various graphics showing about strength properties. In the software, in the configuration of the type, we can find two options for the face milling gears. One's a constant slot width and one's a modified slot width. If we go to the tab process, we can see also then manufacturing with face milling, and we can see the cutter radius, which is described, or the cutter head, which is described in the cutter radius exactly. If we now have a look at another example, face hobbing, but then hypoid as well, we can see in the configuration type, we can see uniform depth, face hobbing, Klingelberg and Oerlikon. This is because of different hypoid iteration algorithms, which are in the ISO 23509 given. When we go on process, we can see face hobbing. We can also see cutter head. It is described by a cutter radius and number of blade groups. Both of them are needed to calculate then the epicycloid lengthwise curvature. Let's go to the overview graphic. In the overview graphic, we can see this typical parallel two-stepped or two-side. We can also see that for hypoid gears, no 3D geometry is available, and we can see then still some graphics about strength properties. Let me have a look also at the straight bevel gears. And straight bevel gears are described in configuration with the three standard options. Here it is selected figure 2, which has the user input available for the addendum and diddendum angles. When we go on process, we see there is no cutter head selection available because it's not manufactured in that same process. And when we go on an overview graphic, so then we can see in the 2D graphic, we can see some specific properties or functionalities in KISSsoft for forged bevel gears. We can see the webbing outside and inside, toe and heel side, and we can see a constant hip clearance, and then we can see the alteration of the pinion. So, and this is a functionality which is available in KISSsoft in the tab modification. There are two modes available. One is a manual input of the data. Let me show a help graphic. So this is how the alterations are defined by a length and a height value. There is a manual input possible, or it's an automatic, or let's say a sizing mode is available as well. So and in addition to this, the contact analysis is available as well for differential bevel gears. And when we do now a calculation, we can see that for the forged bevel gears, now the contact analysis is done on the active flank purely. So it means this is a way to rate the effect on the alterations, and it means of the reduced tooth flank area. So if you're interested in differential bevel gears, there are some options in KISSsoft available. To complete the section of scope of KISSsoft, let's have a look at the drivetrain calculation or the system calculation. We can see here a bevel gear in an industrial transmission, and we can also see here that the load spectrum is defined. And when we now calculate the load spectrum in the system, so, and we go to the component, the bevel gear as a component, then we can see first of all the load spectrum, and we can then further do a calculation of EPG-misalignments using the shafts. So we can see the shaft files are now connected, and now we calculate for these 3 load pins, we calculate the load depending misalignment values. With this release 25, this is also available for differential bevel gears, which are in multi-mesh functionality. So, and what then further will be done, it is then an export available of these EPG values to the GEMS software. First, let us have a look at the results. The results are here. So we have now per load pin in forward and in reverse mode, we have now the EPG numbers, and they are then, for example, exported for further analysis in, for example, in GEMS. I will come to that software. And by an XML file, this is transferred. Let us have a look now also at this XML file. You can see here. So this XML file, it contains the macro geometry of pinion and wheel. and it contains also the 3 load bins which were calculated, and they are then transferred to the GEMS software. In the presentation, there are some slides added about, let's say, some specifics of phase hopping and phase milling. I do not further comment on this. If you have questions about, for example, which manufacturing process is the best one for you, we recommend to contact then Gleason Bevel Gear application engineers. They can consult you best. So I would like to comment a bit now on the 2 software which I mentioned, the KISSsoft and the GEMS software. I would like to highlight that KISSsoft uses a virtual cylindrical gear approach, whereas the Gleason engineering and manufacturing system software uses simulation of machine settings. So, and what typically is the process is that the macrogeometry, load data, and the EPG values, they are transferred into the GEMS software, and there a detailed analysis of the applied cutter head size, of the final blank geometry, or of a blade design is then done, and these data can be transferred by the same interface back to KISSsoft to have a more precise result of using rating standards. On the next 2 slides, there are also some graphs from the GEMS software. We can see there is a development of contact pattern in unloaded tooth contact. There is a rating of a loaded tooth contact analysis using an FE. And also quite important is the blade or the tool design in the GEMS. You can see for each of the Bevel Gear set, there is an, let's say, development necessary of the tool. So the point width must be specifically designed for the slot width of phase hopping, phase milling gears, and as a result, then also the maximum tip radius, inner blade and outer blade are designed, and this is then again the input for the KISSsoft strength calculation. Now I would like to continue with details in strength calculation. In KISSsoft, the standards are implemented as shown here, and I would like to comment a bit about the typical process we recommend. We recommend to use standards, rating standards for the design. Why? The rating standards are very quick, so it allows to get a variation of the macrogeometry in very short time to make sure the base properties of the Bevel Gear are ideal. There is a bit of hesitation of the users against the rating standards, which I would like to comment. And the reputation of standards is a bit bad in terms of accuracy. I want to highlight that at least in the ISO standard, there is ongoing research and also ongoing adaptation of research results into the standard. So we recommend to start with a design by rating standards. Of course, we also agree to have the optimization of a flank topology done in contact analysis. The contact analysis includes and considers also first of all misalignments, secondly the exact flank topology, and this is quite a process to check on the various load cases and how the contact pattern moves under load. And so to avoid the peak loads and edge contacts, this belongs to the design work of a design engineer. In the following, I would like to comment on some parameters which are specifically for bevel gears, to give you an impression of how specific the bevel gear standards are compared to the cylindrical gears. One point is the effective phase width, and you can see in this contact analysis result, you can see that, let's say this is a nominal load. On the nominal load, we can see first of all the load distribution, which is typically for bevel gears quite larger because of lengthwise crowning to cover the various misalignment situations. And this also results then in a shorter effective phase width compared to the nominal phase width. What I would like to comment now is that the design engineer will find in the tab rating, in details, he will find the parameter with typically 85% because this is proposed from the ISO standard. Now it is important to think at it because if you have any larger phase width than the, let's say, 85%, which are a bit conservative, then you enter the larger value and you will see that also correspondingly then the safety numbers will increase. The next parameter I would like to discuss is phase load factor. Phase load factor KH beta is calculated on the first glance quite simplified. It's a factor 1.5 times the mounting factor. Mounting factor is taken from a table, and this typically results that the phase load factor for bevel gears is in a range of 1.5 to 1.7. When we had a closer look at an FE calculation, we counted and we calculated the phase load due to the various contact points, and we came to a very similar result. So this calculation seems to be not too bad. What KISSsoft in addition added is the calculation using the NXE method from ISO 6336, which I used just before in the system calculation. This allows to have a load-depending KH beta value, and also then we can calculate the load-depending misalignment values. Now I would like to look at some specific points in the root and flank calculation. One point I just mentioned before, so don't forget to use the data from the blade design to enter in the KISSsoft. This is the tip radius of inner blade, of outer blade, and how to handle in KISSsoft. Typically, you're in the, let's say, the design engineer is in the mode of designing where the default reference profiles are used. When you want to change, please switch to length and then switch to own input. And now you will be able to enter the exact root radius. And again, you will see then a change in the root safety number, and this also makes your rating standard result more accurate. A specific parameter for Bevel Gear is the tooth thickness modification coefficient. In the Bevel Gear, it's possible because it is defined so that the tooth thickness modification can be changed individually per pinion or wheel. And we can see that this also affects the strength results. And I will now directly go into the software. So we have an example here. We have a tooth thickness modification coefficient. When the user enters a certain backlash, which is required out of his design rules, then the standards, they propose a certain tooth thickness modification for pinion and wheel. These are the calculated values. When we now do a calculation, we see, okay, pinion has a root strength of 1.32, the wheel 1.30. Okay, they are quite close. So maybe you would like to accept, but keep in mind the root safety numbers, they might be a small difference, but when we look at the service life, which is achieved now, we can see it's 555 hours, which is limited by the root service life of the wheel. When now the user does a better balancing between tooth thickness, now let me take the numbers which I prepared for this case. I also want to maintain the same backlash. So if user now uses more balanced tooth thickness, we can see in the numbers, root safety numbers, yes, they are balanced. But more impressive is to see that now the service life has increased. The system service life has increased to 950 hours because of the increased service life of the wheel. And this is an improvement of almost factor 2. So you see this change made a big effect on the service life. The next effect, Bevel Gear specific effect, is the influence of the cutter head radius. And now we need to understand a bit about Bevel Gear specifics. When we have a Bevel Gear using a small cutter, the involute point is placed in the middle of face width. When we use a large cutter, then the involute point is placed out of face width. The interesting part here is to understand that a contact pattern typically tends to go towards the involute point. This means in a large cutter design, the contact pattern will move tendenциally towards the heel, where in a small cutter design, the contact pattern will move tendenциally to the central position. And this has a positive effect on the root strength because a centered contact is preferable for a higher root strength. There are limitations. User cannot apply smallest cutter head. The recommendation is to have the involute versus the outer cone distance in this range, 0.95 to 1.05. And let me now have a look in software, how we can do it. So we have a face milling design, and the current cutter head is 3.75 inches. When we can see the same graphic here. So when we now decide to go on a small cutter design, then we enter the value of 0.95. We press calculate and we get a theoretical cutter head size of 2.7. In the infographic, we can see that the existing cutter heads from Gleason and Klingelberg, they are listed here. And be aware, this is a cutter diameter. So now user has the choice between a 5-inch, which is 2.5, which is smaller than that one, or a 6-inch. So let's now go on a 2.5-inch cutter head. Let's see the previous result of 1.34. Sorry, 1.34. So now we can see an increased root strength of 1.46. However, we are out of the recommendation range. So let's go on a 3-inch cutter head. Sorry, 6-inch cutter head means 3-inch radius. We can see the root safety now is 1.4. Again, this is a typical situation where in the GEMS software then the effect of the various cutter heads will be checked. Is it possible to have an, let's say, a proper cutting? Is it possible to have a proper tooth contact under the various loads? So these investigations are then done in the GEMS software. In the next 2 slides, I just want to list here 2 more parameters. I will not comment further, just to make you aware that the Bevel Gear, Bevel Gear standards, they incorporated many specific parameters to make the rating standard accurate as possible. The last point I would like to comment is the life factors. This is, however, this is a point which is valid for cylindrical gears and bevel gears. Just want to make you aware or remind on the effects that if your current load cycle, number of load cycles is in the infinite life, then it is important to consider the correct life factors or the permissible stresses as per your experience. There are various hypotheses in the gear design available, and let's have a look now. So for this current case, we can see in this case, the number of load cycles is in the infinite life area. And when we now want to consider a different behavior of the life factors, it means not reduced, it means with optimum quality and experience. Then we will find a different result in the safety numbers, so which affects the result quite strongly. We can see again now in the ascent curve how it looks. So I just want to make you aware of this effect. And it is important to be clear what you want to use. To conclude the section of strength calculation, I want to show you the overview of the example files from the standard. There are 3 example files. One is a bevel, 3 are hypoids, and KISSsoft results match precisely or very accurate with the standard. However, it might be that if you have results from Gleason or Klingelberg strength calculations, this might be a little bit different, because maybe other software do not use the ISO standard so accurately as KISSsoft does, or they use own developed methods. So just to let you know, KISSsoft is precise here, and there are always also additional rating methods available. Now I would like to look at the design of bevel gears. When we do a design of bevel gear, KISSsoft provides two functionalities. First, the rough sizing, and secondly, the fine sizing functionality. For rough sizing, there are two approaches possible. We can see one approach by torque constraint, the other approach by a diameter constraint. This one is rather more applied from manufacturing engineers, because manufacturers engineers know the maximum space of the wheel. They enter then the maximum outer pitch diameter of wheel and start the design of the bevel gear from that side. Design engineers typically have torque and speed data, and they start the design from this side and will get the diameter as a result. Secondly, we will look then at the fine sizing functionality as well. So let us now go through this process in the software. When we do a new design, let's go for a face milling design. Let's have a spiral bevel. In the tab process, we set up for face milling, and in rating, just want to change to drive side. We give speed data, we give torque data, and now we can start with the rough sizing functionality. I want to have, for example, 3.2 ratio. These sizing buttons here, they just give a first typical value to start. And now I'm wondering about the results of the rough sizing, number of teeth on the pinion and the outer pitch diameter. However, if I know that my space in the design is different and is limited, I can override and get a new rough sizing design. The next step is then to do fine sizing. And fine sizing starts with update the fine sizing inputs into the fine sizing table. And then user can define on the parameter which he wants to vary on. So in KISSsoft, we give then the minimum, maximum numbers and the step. This is now for pressure angle. Typically also the spiral angle is subject to vary. The face width I typically do not vary, because you can see here, because I keep the outer pitch diameter, I keep constant. This is not a hypoid design, so there is no variation on offset. But for example, I want the software to vary also on the number of teeth on the pinion. In the condition 3, there are some options. For now, I only want to remove the checkboxes, or to have these conditions invalid. And now I press calculate, and now KISSsoft does, based on the standard, a variation of the parameters and gives me, or gives the user, all the variants with all the combinations of the parameters. We can see first the table of results, and in the table we can see many parameters. Many of them are geometricals. geometry parameters, for example, also an overlap ratio is a good parameter for design result, but then also strength results, power losses, and for bevel gear also quite important to consider about the axial and radial forces, because typically the bearing just behind the pinion, it has to cover then the radial forces on the pinion. In the graphic, there is a horizontal axis, which I typically use for a strength result. The vertical axis typically also used as a result parameter. In this case, I would like to apply a force, the radial force on the pinion. And as a color scale, I typically use a design parameter. So, for example, number of T's. And now I can see what is the effect of the number of T's on pinion on the minimum root safety and on the radial forces on the pinion. And I can see here in the root safety, can see a clear dependency on this design parameter, whereas for radial forces, obviously it's insensitive how many T's are on pinion. So this gives me a better understanding how I should do my design. So, and finally, user will pick a result and will use it then for next further analysis. Now I would like to come to contact analysis and misalignment calculation. As said in the beginning, contact analysis is for bevel gear is an important analysis, and KISSsoft implemented the contact analysis on the basis of virtual cylindrical gears. You can see here many slices over the face width, and then the analytical approach of Weber-Banachek is applied. This is an analytical approach and is very fast. The misalignments, they are described by the parameters H, V, and J, or P, E, and G, and they mean actually the components, the horizontal and the vertical component out of the misalignment, which is normal to the contact and actually to the contact force. And this is how the misalignment parameters are defined. The calculation of misalignments is shown here. It is defined so that the current shaft bending is considered and the vector is placed for pinion starting at the middle of face width. The same is for the wheel. Also here a vector is placed, and then out of these the EPG misalignments are calculated. And for example, for X-center, or in the nomination of Klingelberg, is the V displacement. This is then the shortest distance between these two vectors. Design engineers are typically struggling a bit with the detailed definition of EPG calculation. And I'm happy to tell you that now in ISO committee, a project is launched where the EPG calculation and details of it will be standardized. We hope that this will clarify many questions and should be a practical approach then how to use EPG between the design software and the manufacturer software. For the contact analysis, I would like to show you some results, and starting with a straight bevel gear. In KISSsoft, we did a design which is very close to a design from Coniflex Pro, and we can see in the nominal position an identical contact pattern. When we now apply misalignments for pinion and for gear, we can see the corresponding results on the contact pattern between the GEMS software and the KISSsoft software, and this is a very good match. The same we did for spiral bevel gears, and here we struggled a bit more because it was not possible, and this is already the outcome now, it was not possible to apply with the standard modifications. It means lengthwise crowning, profile crowning, spiral angle modification, twist, to duplicate the manufactured topology from conventional manufacturing. In the nominal position, we have a good correlation. We have a good match. When now EPG displacements are applied, we can find differences. Maybe in the unloaded contact, this is still quite good and quite much the same, but for loaded, there are here and there some differences for the P displacement and for the G displacement as well. And let me summarize. So first, what are differences between the software? I want to remind that KISSsoft uses a flank topology defined by mathematical approach, and GEMS uses a flank topology by simulation of machine settings. Also, the approaches are different, but here I'm not sure how big the effect from using different approaches is. I just want to be complete here. Your outcome on this is how to apply it to software. For straight bevel gear, we find a good match and a good confidence in KISSsoft, also using EPG misalignments. For spiral bevel gears, we recommend to use KISSsoft for applications with medium requirements in noise and load distribution, and it provides an assessment. For noise or load sensitive designs as in automotive, aerospace, definitely a simulation by GEMS is recommended. Regarding manufacturing processes, if you use 5-axis milling, then the topology will be defined from KISSsoft, from the 3D model, which then is precise, whereas Gleason or the Gleason software is applicable for conventional manufacturing and 5-axis milling. So this should give you a recommendation how to use the software in what cases. Let me come to the last point, the bevel gear in transmissions. Bevel gears are applied in almost all the fields of application. You can see here a selection of system module files. And the purpose is typically to analyze in static behavior and in dynamic behavior. In the next slides, I would like to give you some points which you should consider. For the static analysis, it's important to consider bearing including stiffness. We can see here two cases. One case is a bending line without bearing stiffness calculated. The other case considers bearing stiffness. And we can see, first, this is a more realistic bending line, and secondly, when we look Considering then the misalignment of the pinion in the middle of face width, we can see a significant difference between the two results. So to consider bearing stiffness is a strong recommendation. Also, shaft and housing temperatures affect the calculation of EPG-misalignments strongly. In KISSsoft, you have the possibility to enter housing and shaft temperature, and we can see now in this green line the axial deformation and misalignment. That this also affects then the position of the pinion shaft in lengthwise. The effect of housing is considered in KISSsoft with a stiffness matrix. We can see the process starting from design through the FEM, then a stiffness file is created, imported in KISSsoft, and then the contact is calculated considering the deformation of housing. Let me show this in the software. So here we have a hypoid rear axle design. We can see the typical arrangement. We can also see the step file of the housing. However, for the deformation of housing, KISSsoft uses the stiffness matrix. Here we can see a stiffness matrix file is connected to it. And when we now calculate, then there is an iteration done between the housing deformation and the static loads on the shaft file. It's already completed now. So, and now we can see that for the shaft calculations, each of the bearing gets a different individual position of the bearing outer ring. And this represents then the deformed housing. This is for static analysis. Let me show you about an NVH analysis of a rear axle. We did this study a couple of years ago, and I would like to give you the steps which are typically done. So it starts with a static design. This model is then transferred into an MBS software. In the GEMS software, the contact of this hypoid gear set was developed, and the 3D models were imported into the MBS software as well. After calculating contact forces in the MBS software, we compared them between MBS and GEMS software, and this looked very, very good in terms of the same results. And out of that, the structural modes were calculated in the MBS, and the acoustic analysis was done, in this case, using virtual accelerometers on the housing, or also a spherical radius can be applied to simulate the audible noise. What we did in this study then, we wanted to verify on this NVH analysis, and each of the Bevel Gear engineer knows that if the pinion is retracted with a mounting distance of 0.1 or even 0.5 millimeters, we will get different noise behavior of the gear pair. And this we did with the analysis as well. We started with a neutral position, had a mounting distance larger by 0.1 than by 0.5, and we could clearly find an a higher excitation in this case, and this gave us a good confidence into an NVH analysis, so that for further designs, an NVH analysis gives a benefit for the engineer to vary then in the simulation, maybe about housing, about the structure. And so we believe an NVH analysis has a good benefit. We come to the end of the webinar. Here you can see on the last slide, you can see then some recommended literature, or what I also use for this presentation. And here I would like to close the webinar as an official part. And now I will look at your questions in the chat, and I will try to answer on them. So there are various questions. One question is, which configuration to be selected for spiral bevel gear, and tips in reverse engineering of spiral bevel gear. Yes, okay, configuration, how, let's say, there are the face milling and face hobbing configuration. How to find out it's a face hobbing or face milling gear? There is a nice trick. If you put a ruler to the heel and to the toe side of the two-stepped, you can find small differences for face milling. And for face hobbing, it remains constant. I agree, by eye, this is not so easy to see, but if you use a ruler, you can find, and then in KISSsoft you set the corresponding configuration type. With reverse engineering, if you want to duplicate even the topology, there are also possibilities in the software. Let me go here. There is possibility to do a reverse engineering of the topology by using topological modifications. There is an example file available here. If you are interested further, please let me know. The next question is the GEMS software included in KISSsoft 2025? No, it's not. Okay. KISSsoft has an interface file, save of course on the GEMS software side, and with this file it's possible to exchange the data on macrogeometry, on the load data, and on the EPG misalignments. Now, the microgeometry is not transferred because of different approaches in the calculation. Please let me know further if you are interested in specific points between GEMS and KISSsoft. The next question is, what is the recommended accuracy class DIN for spiral bevel gear? That's a good question, because this depends strongly on the selected hard finishing method. If you use lapping, lapping achieves DIN quality 8 to 9, to be honest. Yeah. It depends of the hardening process. If there is maybe vacuum hardening applied, distortions can be, let's say, smaller, and also the DIN class can be, let's say, better. Yeah. Whereas for grinding, you end up I would say in DIN 4, 3 to 4. So this is a disadvantage of the lapping. It's quite a nice option for hard finishing, but the achieved accuracy class with lapping is unfortunately a bit worse than for grinding. Then the next question is it possible to directly input Gleason helix set value for ISO standard calculation? Please, some example if possible. If you want to enter Gleason data into KISSsoft software, let me show you. There is a nice possibility, this conversion. Here in this conversion, there is let's say an input field available, which lets you enter the data from a Gleason dimension sheet directly, because there are different definitions between Gleason AGMA approach and the DIN ISO approach. So this should help you. There was a question about can you explain how to import housing? Yes, which was so how to import the housing. There are the two options in the KISSsoft. So first there is the step model. The step model is in the system module is added here, yeah, and then this is for visualization and also for interference check. And in addition, if you want to do a housing deformation in this input fields, then the file is selected with the stiffness matrix. These 2 points are available. It's independent. You can have a housing solely, or you can have a stiffness matrix solely. They are not necessarily needed both to have. Then next question is about, we still have some time, so let me look at the questions. What is the limit of phase width versus module and phase width versus outer diameter? Yeah, that's there are recommended rules, especially for the phase width, not versus outer diameter. It's called phase width versus outer cone distance. Let me try to show you in the software. So this was in rough sizing. When we did rough sizing, you see here we can give a ratio of out of cone distance to phase width. Yeah, then it's 3.5. So typically the phase width is 1/3 of the cone distance. And just to be complete, what is the cone distance? Here we can see. So cone distance is actually, we can see here, in the measured on the cone. Yeah, starting from crossing point to the outer or the mean middle of the phase width. Next question is there interface to KISSsoft Klingelberg software? Yes, currently we are working on it. And if you're interested, please let us have also some examples we want to test on it. So then we are complete. Let's say we have interface to GEMS and we have an interface to KISSsoft Klingelberg software. Okay, this was from the question side. Here is I would like to conclude on this webinar. I would like to thank you for your attention and for your questions, and I wish you a nice day. Bye-bye.